So now we're finally going to talk about ranking acids. We've spent a lot of time here comparing bases, and that's what the rules in the REO mnemonic are for. They're for comparing bases. But the idea here, we've already talked about, is that the stronger an acid, the weaker the conjugate base. And so a stronger acid has a weaker, more stable conjugate base. And so generally, if you got to compare bases, that's what the rules are for. You're ready to go. But if you've got to compare acids, the first thing you're going to do is draw their conjugate bases. Now, one thing to note, I will say that I told you there's a table of pKa's I highly recommend you memorize. And so if you're comparing acids, I'd first just look and see if they're in your table. If they are, then you can very quickly come to a comparison, right? So memorize some pKa's, go from there. So if we take a look at this first example, for instance, I see I've got an alcohol and his pKa is on the ballpark of 16. But then I've got a thiol, and it didn't make my list. It makes some people's list. His pK is around 8. But in this case, it's not on my list, so I'm just going to say it's a question mark. And this is a situation where I should definitely use that REO mnemonic. But again, the REO mnemonic is for comparing the conjugate bases, not for comparing acids. So in this case, the first thing I'll do is draw the conjugate bases of each one of these. So once they donate an H+, this is what you'd have left. And your basic atom would either have a negative charge on an oxygen or a negative charge on a sulfur. And to compare them with the REO mnemonic, the atom rule is first, and there's a difference, oxygen versus sulfur. And in this case, the larger sulfur, so oxygen and sulfur above and below each other on the periodic table, and the larger sulfur is the more stable base, and the more stable base is the weaker base. So he's, again, weaker and more stable. And if he's weaker and more stable, that means his conjugate acid is the stronger acid, which is what we're being asked here. So that's kind of how that works. So let's take a look at another example here. So again, before I set up my REO mnemonic, I might just check and see if I know the pKa's of these. And this first one, the functional group is a carboxylic acid. pKa is in the 4 to 5 range. Second one, here's an alcohol, and a typical alcohol has a pKa in the 16 range. And since these both made my list, I might just simply go straight into circling the one on the left. So this chlorine, we will find it does have an influence, but not as significant as we might think. So, but let's use that REO mnemonic anyways. We technically didn't need it here if we have memorized the pKa's I recommend you memorize, but let's go through it. If we draw the conjugate bases for these acids, you get a negative charge on an oxygen versus a negative charge on an oxygen. So going through the REO mnemonic, the A rule, atom rule, doesn't help us. It's negative charge on oxygen, negative charge on oxygen. It's the same atom acting as the base in either case. So then we move on to R in REO for resonance. So in this structure on the left is going to have two resonance structures. That negative charge is going to be shared on two oxygen atoms. The one on the right is not going to have any additional resonance structures, so just the single structure. And that negative charge is completely on one oxygen. So the one on the left, due to resonance, is the more stable base. And the more stable base is the weaker base. And the weaker base comes again from the stronger conjugate acid. So it just confirms what we'd learned earlier by just comparing pKa values we'd memorized for functional groups. Now, one thing to note, you might be like, well, what about that chlorine, Chad? We never talked about it. And you're right, we never talked about it. That was the next rule. So we give you these rules in order of descending importance, and that's why you follow them in order. The atom rule didn't give us a difference, but resonance did. And the reason we stopped there is resonance generally is more important than the inductive effect. And so if there's a difference at resonance, that trumps anything you might learn at the inductive effect. Now, we said earlier that the pKa for this alcohol was 16. Well, for a general alcohol, it's 16. It turns out this one, having that chlorine, the inductive effect does play a role. It's actually 14.3, but this is still much weaker as an acid than our carboxylic acid at 4,5. So just demonstrating that we follow these rules in order because resonance generally is more important than induction. So let's take a look at yet another comparison here. And if we look at these two, and again, they are both on our list here. So the first one here is a carboxylic acid. So his pKa is in the 4 to 5 range. And the second one here is going to be a phenol. So in fact, it's just plain old phenol. And so his pKa is equal to around 10. And right off the bat, we can be like, oh, the lower pKa, that's our stronger acid. And we wouldn't have needed to use the REO mnemonic. Now, I want to talk about that REO mnemonic for a sec, though. And the first thing we do is draw the conjugate bases. And I've already drawn them here, and you'd have seen that we have a negative charge on oxygen versus a negative charge on an oxygen, and our atom rule would not have done us any good. So we'd move on to resonance in REO, and in this case, this is where we'd see the difference, but it wouldn't be so obvious what the deal is. So here we've got two resonance structures, and the negative charge is shared between two oxygen atoms. But in this other one, we have four resonance structures, and the general rule is like, oh, more resonance, more stable. Well, it's not quite so simple here. So even though it's got four resonance structures, it's only sharing the negative charge on one oxygen and then three carbon atoms. And so the question becomes, is it better to share the negative charge on two oxygen atoms that are both electronegative, or on one electronegative oxygen and three not so electronegative carbon atoms? And there's not an obvious answer here. It's something that you might only know with experience. We might try to intuit a little bit or something like that. But the truth is, you just got to be told this once and then remember it. And the idea is that it turns out having the negative charge shared between two oxygens is significantly more stable than sharing it on one oxygen and three carbons. So on the left there, even though it's the fewer resonance structures, this is the weaker and therefore more stable conjugate base, and the weaker, more stable conjugate base again has the stronger conjugate acid. So this is one of those examples where the rules might not be completely obvious of your choice, and so memorizing some pKa's would totally benefit you in just such a case. All right, so let's take a look at one last example here, and we've got a terminal alkyne and an amine, as the case may be. And before we look at the REO mnemonic, we should look to see if these made our list. Well, in this case, we see we've got a terminal alkyne, and so the pKa is somewhere around 26. And over here, we've got an amine, and an amine specifically is not on here, but it would be comparable to ammonia here. And so his pKa might be in the ballpark of 37 or 38 here. And so right off the bat, this would be our lower pKa and our stronger acid, and we wouldn't need the REO mnemonic. And that's a good thing. The reason I recommended you memorize these pKa's is because the REO mnemonic is not foolproof, and there's no set of rules that is foolproof. And we'll see why this is the case here in a second. So if we did try to use that REO mnemonic here, so ARIO, so we draw the conjugate bases. So this guy gets deprotonated, negative charge on the carbon. This guy gets deprotonated, leading to a negative charge on the nitrogen. And so we'd go to the atom rule, and we'd be like, okay, negative on carbon, negative on nitrogen. Negative on nitrogen would be more stable, and more stable because he's more electronegative, and that would be the weaker, more stable base. But obviously, from our earlier determination with the pKa, we usually say the weaker base has a stronger conjugate acid, but we're getting the exact opposite determination. And so it turns out our atom rule here would have led us astray, and it turns out there's no resonance in either one, there's no real induction going on with either one, but the orbitals are also playing a role here. And so in this case, your nitrogen right there is sp3 hybridized, but your carbon over here is sp hybridized. So based on the atom rule, it looks like nitrogen would be a weaker base, but based on the orbitals rule, an sp hybridized atom should be weaker than an sp3. And in this case, it turns out the orbitals rule actually ends up being more important than the atom rule, which is completely unexpected. We usually follow these rules in the order that we do based on their relative importance. And so in this case, the REO mnemonic would lead you astray, but again, had you already memorized some pKa's, you would have been great. And so again, that's the whole point with memorizing some pKa's, is that no set of rules, including the REO mnemonic, is 100% foolproof. But if you've already memorized some pKa's, there's some tricky examples that I can't trip you up with because you'll already know their pKa values from the get-go.